Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatro from the Department of Physics and Astrophysics, University of Delhi, Delhi, India. Today we are going to discuss about a module named Formulation of Second Harmonic Generation using Classical Harmonic Oscillators, which belongs to the chapter Nonlinear Optics. From the paper Characterization Techniques for Materials 2. The learning objectives from this module is first, introduction to second harmonic generation, and second, we will learn about mathematical explanations and examples of the second harmonic generation. Then, how to formulate this second harmonic generation using harmonic oscillator. In relation to polarization on the electric field, we have learned that the bulk polarization in intense field depends on the linear, second, third and higher order nonlinear susceptibilities. The linear susceptibility coefficient chi1 is dominating in weak fields and gives rise to optical processes such as Raman and relay scattering. The phenomenon of birefringence, that is double refraction, etc. The nonlinear susceptibilities chi2 and chi3 become significant at intense fields and control the nonlinear processes such as the first one, some frequency generation denoted as SFG, in which laser photons of frequency omega 1 and omega 2 are combined into single photon with frequency omega 1 plus omega 2. The second of the kind is second harmonic generation denoted as SHG, where two laser photons at frequencies omega 0 are converted into a single photon of frequency 2 omega 0. And the third one is the third harmonic generation, that is THG, where omega 0 plus omega 0 plus omega 0, that means it gives 3 omega 0 frequencies. The chi2 governs the SFG and SHG processes, and the third order susceptibilities chi3 governs the THG as incoherent anti-Stokes Raman scattering. The second harmonic generation, also called a frequency doubling or abbreviated as SHG, is a nonlinear optical process in which photons of same frequencies interact with a nonlinear material and effectively combined to generate new photons with twice the energy and therefore twice the frequency and half the wavelength of the incident photons. It is a special case of some frequency generation. Generally, in centrosymmetric materials, the crystallography is defined by a point group that contains an inversion center as one of its symmetry elements. In centrosymmetric media, which have inversion symmetry, so that the properties of the medium are not altered by the transformation r tending to minus r, and the PE function must have a odd symmetry, the polarization and electric field relation, so that the reversal of E results the reversal of P without any other change. The second order nonlinear coefficient D must then vanish, and the lowest order nonlinearity is of third order. The second harmonic generation cannot be demonstrated in the centrosymmetric materials because of the inversion symmetries in polarization and electric field. The commercial uses of second harmonic generation includes the laser industry that makes green lasers of wavelength 532 nanometer from a source of 1064 nanometer through a bulk monopotassium phosphate crystal, generally noted as KDP crystal. Also, the second harmonic, often called frequency doubling, is a process in radio communications and has been used with frequencies in that megahertz range. The effect of second harmonic generation is also used in biological and medical sciences for taking high resolution optical microscopic images of collagen, generally found in most load bearing tissue structures. Schematics for second harmonic generation. Second harmonic generation can be visualized by considering the interaction in terms of the exchange of photons among various frequency components of the field. Under proper experimental conditions, the process of second harmonic generation can be so significant that nearly all of the power in the incident beam at frequency omega is converted to radiation at the second harmonic frequency 2 omega. The energy level diagram of the second harmonic generation process is schematized in the figure, where the system is shined with a laser light of frequency omega and generates a frequency of 2 omega. Equation of second order susceptibility. Consider a laser beam with electric field strength represented as E, the function of time, is equal to e to the power minus I omega t plus the complex conjugate. Let this beam is incidented upon a crystal for which the second order susceptibility chi 2 is non-zero. The nonlinear polarization produced in such a crystal is given by p square as a function of t is equal to chi 2 e square, which is a function of time, which is equal to chi 2 whole multiplied by e omega e to the power I omega 1 t plus e omega e to the power minus I omega 1 t plus E0 whole square, which is equivalent to E omega square multiplied by e to the power I 2 omega t plus e to the power minus I 2 omega t multiplied by e omega square plus 2 E0 e omega multiplied by e to the power I omega t plus e to the power minus I omega t plus 2 e omega square plus E0 square whole multiplied by chi 2. The first term is represented as the second order polarization and consists of a contribution at zero frequency, and the contribution at frequency 2 omega is the second term. According to the driven wave equation, this can lead to the generation of radiation at the second harmonic frequency. The second term oscillates at omega and causes a variation in the refractive index in the medium. This is termed as linear electro-optic effect. This third term doesn't oscillate and is conversion of the oscillating field to a static field and is known as optical rectification. Examples of second harmonic generation. Example 1. The second harmonic generation could be interpreted as a coherent optical process of radiation for dipoles in the material and depends on the first term of the expansion for polarization as represented in equation 1. The dipoles are oscillated with the electric field of frequency omega and it radiates the electric field of frequency 2 omega as well as omega. So, the near infrared input light comes out as near UV lights and the schematics are represented on the screen. As example 2, one common use of second harmonic generation is to convert the output of a fixed frequency laser to a different spectral region. As an example is neodymium doped yttrium aluminum garnet, generally known as NdYAG, is a crystal that is used as a lasing medium for solid state lasers. This NdYAG laser operates in the near infrared at a wavelength of 1060 nanometer. Second harmonic generation is routinely used to convert the wavelength of the radiation to 530 nanometer. Harmonic oscillator. Let us consider a linear harmonic oscillator. This for the static one-dimensional harmonic oscillator model and applying static electric field to a charge on a spring makes the spring to stretch. The schematic is shown in the figure. The applied electric field can be so large that it becomes unraveled and leads to enharmonic terms, but we assume the field is small enough to keep the spring intact. This is analogous to a molecule where the electric field is large enough to strongly displace the electrons from their equilibrium positions, but not strong enough to ionize the molecule. A free body diagram illustrating the forces acting on the charge is shown in the diagram. The force on the charge due to the electric field could be expressed as Fe is equal to QE, where Q is the charge of the electron and capital E is the applied electric field. The restoring force due to the spring could be written as F subscript S is equal to K into X, where K is the force constant of the spring and X is the elongation. The force on the charge due to the electric field is balanced by an opposing force due to the tension of the spring. At equilibrium, the forces are equal to each other, that is, F subscript S is equal to F subscript E. Now, substituting the forces from the equation, we got Kx is equal to Qe, and solving for x, we got x is equal to Q divided by K multiplied by E. And using the definition of the dipole moment, we know P is equal to x multiplied by Q. That means P is equal to Q square divided by K multiplied by E. So, the linear susceptibility alpha can be defined as alpha is equal to Q square by K. That makes the dipole moment P is equal to alpha E. For n number of springs per unit volume as shown in figure, we got the chi1 is equal to n times alpha. So, by putting the value of alpha, we get chi1 is equal to n times Q square divided by K. The susceptibility is linear with respect to n for low concentrations. However, as n becomes sufficiently large, the susceptibility diverges from linearity as represented in the figure. In systems such as di-doped polymers, deviations from linearity is a sign of molecular aggression. Nonlinear harmonic oscillator. Now consider the nonlinear harmonic oscillator model. Here in the system, the potential has a quadratic dependence on the displacement x. The real systems deviate from the quadratic potential of a simple harmonic oscillator when the amplitude of x gets large. In this limit, we can approximate x is small when the electric field E is small. Now the spring force is F subscript S is equal to K1x plus K2x square, where K1 and K2 are force constants or spring constants. In equilibrium, the spring force is equal to electric force, so that K1x plus K2x square is equal to Q multiplied E. Now dividing the equation by K2, we get x square plus K1 divided by K2x minus Q divided by K2 multiplied by E is equal to 0. Solving for x, we get x is equal to minus K1 divided by 2K2 plus or minus half square root of K1 divided by K2 whole square plus 4Q divided by K2 multiplied by E. Now factoring out K1 divided by K2, we get x is equal to minus k1 divided by k2 whole multiplied by 1 minus or plus square root of 1 plus 4q divided by k2 multiplied by k2 divided by k2 whole square times E. For a small electric field, we can expand the argument and get x is equal to square root of 1 plus 4q divided by k2 multiplied by k2 divided by k1 square multiplied by E, which is equal to 1 plus half 4q divided by k2 multiplied by k2 by k1 square times E plus the higher order terms. Using this series expansion of the square root 1 plus x to the power half is equal to 1 plus half x minus 1 by 2 x square plus so on, and keeping only the negative root because it yields the correct linear result. Then we get x is equal to k1 divided by 2k2 times half times 4q divided by k2 multiplied by k2 by k1 square times E plus the higher order terms, which can be represented as x is equal to q by k1 times E plus the higher order terms. This is the same result as the linear case where alpha is equal to q square by k. In bulk material, the polarization is given by P subscript I is equal to Pi0 plus chi ij1 Ej plus chi 2 ijk Ej Ek plus the higher order terms, where Pi is the electric dipole moment per unit volume. For a molecule, the quantum description of volume is not a well-defined concept. Thus, it is more appropriate to characterize a molecule in a static electric field by its dipole moment and is given by small p subscript I is equal to mu I plus alpha ij Ej plus beta ijk Ej Ek plus the higher order terms, where small p I is the dipole moment of the molecule, mu I is the static dipole moment, alpha is the first order molecular polarizability, and beta is the second order molecular polarizability. Here chi ijk can be calculated from the dipole moment of the molecule and is given by chi ijk nth order is equal to n divided by nx factorial, ny factorial, nz factorial multiplied by del np divided by del ej del ek, where p is the dipole moment of the molecule and ni represents the number of fields polarized along the ith Cartesian direction. This leads to chi 1 is equal to n alpha, which is equal to n multiplied by q square divided by k1 and chi2 is equal to half del square p divided by del E square at E is equal to 0, which is equal to minus n q cube divided by k1 square multiplied by k2 by k1, where n is the number density. Note that as k2 tends to 0, chi2 tends to 0 in arrangement with the fact that the nonlinearity originates in k2. The third order susceptibility depends quadratically on k2 and can be represented as chi3 is equal to 1 by 6th multiplied by del qp by del E cube at E is equal to 0, which is equal to 2n q fourth divided by k1 cube multiplied by k2 by k1 square. Now, the units of susceptibilities in Gaussian units, chi1 is dimensionless and chi2 is represented as centimeter cube per org to the power half, and chi3 is equal to centimeter to the power 5 divided by org. Next, we will learn about electro-optic effect. Certain materials change their optical properties when subjected to an electric field due to forces that distort the positions, orientation, or shapes of the molecules constituting the material. The electro-optic effect is the change in refractive index resulting from the application of a DC or low frequency electric field. A field applied to an anisotropic electro-optic material modifies its refractive indices and thereby its effect on polarized light. This electro-optic effect originates from the second term in the nonlinear polarization that represent the oscillation at frequency omega and causes a variation in the refractive index of the medium. The dependence of the refractive index on the applied electric field takes one or two forms of the following. First is Pockels effect. Here, the refractive index changes in proportion to the applied electric field, in which case the effect is known as the linear electro-optic effect or the Pockels effect. Here, n is directly proportional to the electric field E, where n is the refractive index of an electro-optic medium and E is the electric field. The most common crystals used as Pockels cells include LiNbO3, LiTaO3 and CdTe, cadmium telluride. And next is the Kerr's effect, where the refractive index changes in proportion to the square root of the electric field, in which case the effect is known as quadratic electro-optic effect or Kerr's effect. Here n is directly proportional to E square. The change in the refractive index is typically very small. Nevertheless, its effect on an optical wave propagating a distance much greater than a wavelength of light in the medium can be significant. If the refractive index increases by 10 to the power minus 5, for example, an optical wave propagating a distance of 10 to the power 5 wavelengths will experience an additional phase shift of 2 pi. Now let's study about the applications of electro-optic effect. The materials whose refractive index can be modified by means of an electric field are used for producing electrically controllable optical devices as indicated by following examples. The lenses of controllable focal length could be fabricated from a material whose refractive index can be varied. A prism whose beam bending ability is controllable and can be used as an optical scanning device. The light transmitted through a transparent plate of controllable refractive index undergoes a controllable phase shift, and the plate can be used as an optical phase modulator. An isotropic crystal whose refractive indices can be varied serve as a wave retarder of controllable retardation. It may be used to change the polarization properties of light. A wave retarder placed between two crossed polarizers gives rise to transmitted light whose intensity depends on the phase retardation. The transmittance of the device is therefore electrically controllable so that it can be used as an optical intensity modulator or an optical switch. So these are useful components for optical communications and optical signal processing applications. So students, let us summarize what we have learned in this module. We have learned about the second harmonic generation process when an incident light passes through a nonlinear medium. New photons of frequencies with double than the incident frequency can be generated, and applications of second harmonic generation finds its recognition as an important mode of microscopy used in biological researches and to probe the electrical conductivity of nerve cells. When the number of molecules increases, the linearity curve diverges beyond the critical displacement, showing the nonlinearity in its quadratic potential displacement curve, and hence the atoms get ionized. The general formulation of susceptibility gives us units of second, third and higher order susceptibilities, and the unit of mostly used second order susceptibility is centimeter cube divided by arc to the power half. Thank you.